From the moment you turned on your cell phone or computer and opened this video, a series of operations and processes occurred. These operations and processes are carried out through mathematical instructions to solve a given task, which we call an algorithm. Or, if you Google it, a set of rules to solve a problem in a finite number of steps. The technology as we know it today is based on increasingly powerful algorithms that perform a wide variety of tasks. But there is one algorithm in particular that completely changed the course of technology and especially communication. We cannot deny that technology and communication have an almost symbiotic relationship. For example, think about the form of communication I am having with you at this very moment, as I speak through a video on a screen. This would not have been possible just 100 years ago. And every time there is a major change in the direction that communication takes, the impact on society is sure to be immense. Just look at how inventions that revolutionized communication from the telephone to the television and the internet have impacted our daily lives. Wi-Fi, 5G, audio, video, everything we know today is important for us to communicate the way we do. But there is a great secret behind all of this. Something that not only enables our modern communication but goes beyond what we imagine. A key role in preserving world peace. Some researchers suggest that it was thanks to this secret that a catastrophe with unimaginable proportions, such as a nuclear war, was potentially avoided. But first, we need to talk about signals.
Hey, Pedro here. This video you are watching was originally in Portuguese, my native language. This is the attempt of our team to translate it to English, and I sincerely hope you enjoy it. Your feedback is extremely important to us. Now, back to the video.
In the context we are discussing, a signal is a variation in time or space of some physical quantity that propagates information. Some types of signals can be electromagnetic waves containing information such as amplitude and frequency. Think of light or radio. Other signals through electric currents, such as audio signals in a wire, are captured by the receiver through information like voltage and power. Generally, you will get a graph like this one here, where the x-axis is some physical property, and the y-axis is time, or perhaps space in some situations. This is a relatively simple example, but these graphs can be complex, containing multiple dimensions. Even images can be seen as a multidimensional signal, as each pixel in this image here contains information such as color intensity. For example, in the RGB system, each pixel is an element of a matrix, and each element is a vector with 3 numbers from 0 to 255, representing the proportion of each color. R for red, G for green, and B for blue. The point I want to make clear is how signals and the transport of information are connected with communication. When you listen to an audio from your friend or when you see a photo of a crush, several of these signals have been processed, transported, and reached you. Of course, we can expand this discussion to videos as well, about how cameras capture images and how the microphone is picking up my voice. And here I can even show the signal, that is the information of the amplitude as a function of time. In the case of this video, it looks like this. There is a processing of these signals from the moment they are received by a receiver until they reach your home, being transmitted by a screen and by the speaker. And here we arrive at the key piece of this entire discussion, one of the most important tools in mathematics that you use all day long without even knowing it. These are the famous Fourier transforms. You may have never heard of them, but I am absolutely certain that you have depended on something that uses the famous Fourier transforms, as they are everywhere. Imagine that you have a signal that you want to transmit. And to simplify, I will consider that it is an audio signal that could be a song or even the audio of this video here. But it can be any signal you want, whether spatial or temporal, or in as many dimensions as you wish. In the case of my chosen signal, we have amplitude as a function of time, something known as volume.
Imagine that you want to take my audio and change my voice so that it sounds like I used helium gas.
If you have ever worked with any audio or video editing program, you know that you will need to change the audio frequency to higher frequencies. The problem arises because you cannot obtain information about the frequency to change it if you only have amplitude available. This becomes complicated because, as you can see, the signal seems to have different waves mixed randomly and not something well defined. I think it's a good idea to define frequency as the number of times something repeats in a unit of time. And in this case, it could be the number of times the amplitude reaches the value x. But there are several amplitude values that the audio has in this time interval of the video. Which value should we choose? Which one will you change to alter my voice with helium? And this is where the magic happens, in one of the greatest insights in the history of mathematics. In 1822, the physicist and mathematician Joseph Fourier concluded that any function can be described by a sum of sines and cosines. Okay, maybe I got a little too excited. So let's break it down. You have probably seen sines and cosines in school, and these functions vary between -1 to 1 and are generally represented like this. These functions have properties such as amplitude, frequency, phase, period, and length. What Joseph Fourier realized is that any function can be a combination of various sines and cosines, each exhibiting different properties. A sine function with such an amplitude and frequency, added to another function with its amplitude and frequency, added to another function with its amplitude and frequency, gives the function you initially have. It's as if you could break a function into different parts that give you more detailed characteristics, like frequency, which we mentioned before. So, basically you get the frequencies and amplitudes of each wave, sine and cosine, that make up the original function. That problem you had before, wanting to change my voice but not having the necessary information to do so, is solved now because you have the frequencies, and you just need to alter them. And this process is called the Fourier Transform. And we can see it as follows. We are in a space defined by something as a function of time, and we move to a space defined by something as a function of frequencies, the so-called Fourier space. And as a note of curiosity, if we are dealing with something in terms of space, like in an image, we call the frequencies modes. But the process is exactly the same. And just to give you a taste of it, this entire tool is described by this simple equation here. And if after altering my voice you want to return to the original audio signal, just apply the inverse Fourier transform, which, as the name suggests, does the reverse process. I have already mentioned an application here, which is precisely to manipulate and edit audio, being able to change the frequency, remove noise, among many other things. In fact, this is how audio is processed in computers and other devices. So you can only listen to this video and use streaming services because of the Fourier transforms. Other applications include image and video processing, which also benefit from the application of Fourier transforms for editing or communication. Or even when you reduce the size of an image or edit it, you use filters, Fourier will be present. In medicine, Fourier transforms are also used for the analysis and processing of tomography or magnetic resonance images. And I believe that the most important thing for you to know right now is that your Wi-Fi connection depends on Fourier transforms, as do mobile data, 4G and 5G. So you can already get an idea of the importance of this mathematical tool, but trust me, it goes even deeper than that. While the Fourier transform is a powerful tool, it can also have a very high computational cost, especially when working with many frequencies at the same time. Since data transmission depends on the Fourier transform, it is natural that something very efficient and very fast is required. Imagine having to walk around with a gigantic computer to hear hot gossip from your friend on WhatsApp because the phone wouldn't be able to process everything on its own. Therefore, algorithms to speed up this entire process that I described have been introduced, and one of them is called FFT, Fast Fourier Transform. What was not expected is that this technique would simply change the course of technology forever and could even prevent a war. The idea is relatively simple. Use the symmetries present in the Fourier transforms to speed up the calculation of the transforms. It starts by separating the transforms into components, considering even and odd numbers. Each time the components are separated, they can be divided again in a technique called divide and conquer. We keep doing this until we reach a limit, and it becomes possible to calculate the entire Fourier transform with ease. Basically, when the Fourier transform is divided into these two components, it is broken down into smaller and easier problems to solve, and thus the efficiency increases. And furthermore, the FFT also uses the so-called butterfly operations, or the butterfly method, to avoid redundancy and take advantage of components that have equal multipliers. The efficiency and speed of the FFT make operations that take seconds last only milliseconds. And this difference may not seem that significant. But it becomes even more impressive when you remember that thousands or even millions of such operations are needed to perform the entire Fourier transform. The speed and low computational cost of the FFT make it a powerful algorithm that can run on practically anything, whether a supercomputer or a cell phone. Without FFT, all data information exchange would be extremely slow. For each signal received, whether through Wi-Fi or 5G, we would have a series of very time-consuming operations that would make your phone's internet seem like it was from the Stone Age. Not to mention the time your own device would take to process audio, images, and videos. The point I want to make is, all this flow of information that we know today, the speed at which we receive and do things, would not be possible. Everything. Absolutely everything from internet speed to data processing would definitely take much longer than acceptable. And you might even think about how this would affect communication. Today we are used to messages arriving almost instantly. And so I leave you with this thought. How would the advancement of technology and communication be today without FFTs to accelerate the exchange of information? Would you be able to watch this video? Would YouTube itself exist as it does today? It's no wonder that FFTs are given the title of the most important algorithm ever created. And the story goes deeper than that, because FFTs played an important role in preventing a nuclear war. In the second half of the 20th century, there was a tension between the United States and the Soviet Union, which was called the Cold War. I could make many videos about the Cold War, and I did, but the aspect I want to focus on here is the arms race, where both sides were developing nuclear weapons. At the same time that nuclear weapons were being developed, ways to detect potential enemy missiles also needed to be developed simultaneously. One of the essential parts was radar signal processing, which could obtain signals from objects through electromagnetic waves. With this in mind, the United States developed a system called PAVE-PAWS, which aimed to detect missiles launched against the country. And for that, PAVE-PAWS had to be fast and efficient, as we are talking about supersonic missiles, and detection time was a matter of survival. And as I already mentioned in the video, the best way to analyze and characterize signals is by using Fourier transforms, which were the basis of the PAVE-PAWS operation. But the process was so slow and complicated that they soon realized the system was incapable of detecting missiles in real time, which made it practically useless. And to make matters worse, the Soviet Union had developed a similar system, but much faster than PAVE-PAWS, called Galosh. For the United States, this resulted in a Soviet advantage, as they could detect missiles much more quickly than them. And knowing this, the American government called the mathematician James Cooley to participate in the Vela Uniform project. The interest in this specific mathematician was because he discovered one of the FFT techniques called the Cooley-Tukey FFT algorithm, which is the most used technique to this day. The mathematician's role in the project was to find ways to apply FFT and speed up the detection and characterization of enemy nuclear tests and missiles. And with his work, PAVE-PAWS was now much faster and could compete with the Soviet system. Both were capable of detecting any enemy movement in real time when it came to missiles and nuclear tests, reducing the chance of false positives. And with the FFT, the tension on the part of the Americans decreased, as part of it was precisely due to not knowing what the next step of the Soviet Union would be. And also not knowing in real time whether a missile had been launched or not, with the risk of the old algorithm making mistakes by giving false positives or false negatives. And an example of this happened in the Soviet Union, when a false positive signaled that the United States had attacked, and if it weren't for the officer Stanislav Petrov, who reviewed the signals a second time, a war could have occurred. And that is why it is common for FFT to be called the algorithm that prevented a nuclear war, as without this algorithm the consequences could have been devastating. And you might even find people who argue that if FFT had been implemented earlier in human history, we could have avoided other wars and accidents. If you have seen the movie The Imitation Game, which tells the story of Alan Turing, you can probably imagine the applications that FFT would have had at that time. FFTs show how something that barely crosses our minds, like the performance of an invisible algorithm, can have enormous impacts on our lives and even on a global conflict. Think about how many things could have gone wrong if FFTs had not been developed and the algorithm had not been applied in so many different areas, from medicine to communication security. Not just in technology, but in the whole world. After all, a war always has tragic consequences for everyone. It is very possible that you wouldn't even be watching this video today, and that everyone we know today would still be a few decades in the future, waiting for us. It is no exaggeration to say that FFTs have changed the world, especially when we see how dependent on the internet we are. From medical exams to YouTube, from saving lives to entertaining them, we owe everything to FFTs. And this is one of the examples of how mathematics can do incredible things in the world and even help save it. Thank you very much and see you next time.